Hi guys, and welcome back to my channel. In this video we're going to be further discussing solid state chemistry, and specifically we're going to be talking about insulators and semiconductors, and with more focus on semiconductors, and then I'm going to talk briefly about superconductors at the end, but mainly we're going to be focusing on semiconductors and how, in the previous video I discussed band theory, right, and the molecular orbitals that went into creating bands, and I'll give a little reminder about that in the beginning. But if you haven't watched that video, you should watch that first. That was called Introduction to Solid State Chemistry with a focus on metals, right? So we're going to be applying that now, applying that theory we learned in that previous video to now analyze the properties of semiconductors and insulators. All right, so this is just a reminder from last time. If you haven't watched that video, please watch that video. But essentially, we have these bands. When we look at, a metal or a semiconductor or an insulator, we're discussing these energy bands, right? So there's a combination when we have a huge, like a solid of metal or a semiconductor or something. These atomic orbitals on every one of these atoms combine together, right? So these combinations of atomic orbitals in a crystal structure, they superimpose and form a bunch of molecular orbitals, and they're so close in energy, and there's so many of them, that we just discuss the entire band in general, right? So they form a nearly continuous energy range of orbitals, which we call just an energy band. And some vocab from last time that you're going to need to know. Conduction band is an empty or incompletely filled band of molecular orbitals. A valence band is a full band, and the band gap is basically the energy difference between the valence and conduction bands, or the range of energy in which there are no bands, right? That's another way of putting it. So here's a little image of the three different types of materials. Right, so we have metals, which we talked about extensively last time, where you can see that the conduction band, there is just a conduction band, right? And the conduction band is partially filled. So with the metal, we have conduction band partially filled. And what does that mean, right? That means that there's essentially no band gap, because the energy to go from, from a part of the filled conduction band to an empty part of the conduction band is almost like infinitely small, right? Because I can take the very top of the filled and the very bottom of the empty, and that's my band gap, and that's like basically infinitely small, right? And that's the reason why metals can conduct so well, because to go from the valence band to the conduction band takes a very, very little amount of energy, right? But now if we look at a semiconductor, for instance, we can see that there's a small tiny gap between this valence band. The valence band is the totally filled band at the bottom, valence, and conduction, which is the partially filled or empty. And we can see that in this scenario, it is empty, right? So we have our conduction band being empty. So in order for an electron to go into the conduction band and therefore be conductive, right, we have to take it and excite it across the small gap. And that gap is called the band gap. And if I look at an insulator, right, we have a much larger gap than a semiconductor. So essentially the differences between all of these materials the differences in their properties are due to the differences in the band gap. How much energy is it going to take for me to excite this electron into a conduction band, right? And that's what matters when I'm looking at the different properties of these materials. Okay, so we're going to talk briefly about, let's go more into insulators now, right? So with an insulator, I sort of mentioned this, but there's a large band gap. And what does that mean? We can see in this picture, it's a little bit more clear. We have this conduction band up top, which is empty, right? We have the valence band at the bottom, which is filled. And we have this band gap, the energy difference between the two. So an electron in the valence band can get excited to join the conduction band, or when energy is inputted, right, this electron can jump from the valence to the conduction band, and that'll make the electron, conductive, right? But because this band gap is so large in an insulator, electrons in valence bands can only be excited in the conduction band with a large input of energy because there's a big band gap. And that essentially means that electrons are not mobile. And that's why insulators are not not conductive, because it takes so much energy to excite them into the conduction band that it's not very favorable, right? So that's an insulator. Huge band gap, not super interesting because you know, it's hard to excite the electron into the conduction band. All right, so semiconductors have a lot more, I think, interesting nuance to them, right? So we're going to discuss intrinsic semiconductors first, and then we're going to discuss doped semiconductors, right? So let's first start with intrinsic semiconductors. And what does that mean, right? Intrinsic semiconductors means that we have just, a pure substance, and it has semiconducting properties. And semiconducting properties means that our empty conduction band lies close in energy to a full valence band. So this is like the middle ground between an insulator and a conductor. Insulator, we had a huge band gap. A conductor, we had basically no band gap, right? So with the semiconductor, we have a small band gap, and this gives some intermediary properties. So for example, if we look on this picture, we have diamond here, and you can see that we have this valence band and this conduction band, and we have a band gap, right? And diamond is not very conductive. It's more of an insulator than a semiconductor. But if I look at silicon, and this is like the classic example of a semiconductor, we have a much smaller band gap. And you can see that visually, right? Between the conduction and the valence band, it's only 106 kilojoules per mole rather than 530 kilojoules per mole, right? So what's interesting with semiconductors, right, is because this band gap is small, what can happen is that thermal energy can excite electrons into the conduction band. So thermal energy can excite electrons into the conduction band, and therefore then the electrons are conductive and can travel through the solid and conduct electricity and, all that good stuff. So this gives semiconductors an interesting property when compared to regular conductors. The resistance of a semiconductor will actually decrease as the temperature increases. Why? Because as you increase the temperature, right, more electrons can jump up into the conduction band, and the semiconductor will become more conductive. Whereas in a metal, right, the opposite will happen. As the temperature will increase, the vibrations of the metal nuclei are going to increase, and what that's going to do is we're going to have more of these nuclei sort of bumping into the electrons, and the electrons are trying to move throughout the solid, so that's going to reduce the conductivity. So that gives semiconductors and metals this interesting opposite property, right? With metals, your temperature increases and your conductivity decreases. With semiconductors, your temperature and conductivity are directly related. Okay, another interesting thing to point out is the differences between diamond, silicon, and germanium, right? So diamond is made from carbon, silicon, obviously silicon, and germanium, again germanium, right? And this basically is looking at elements going down the group, right? Carbon is the highest group, or sorry, the highest period, elements going down the period. So we're going lower one period each time, and we're going down the group. So I misspoke a few times there, but we're going down the group, and so carbon will be the highest period, silicon will be the next highest period, and germanium is the lowest. So if we look at the band gaps between the different, between diamond, silicon, and germanium, we see that diamond has a much larger band gap than silicon, and silicon has a larger band gap than germanium. So this is interesting, right? As we go down the group, the band gap is reducing. What does that mean, right? So we see that diamond's an insulator, silicon and germanium have smaller band gaps and are semiconductors. But why do we have these smaller band gaps as we go down the periodic table? Silicon and germanium, right, they're bigger atoms than carbon. And what does that mean? That means when they bond together, right, for example, like silicon-silicon bonds or germanium germanium bonds, these bonds are going to be much weaker because these atoms are much bigger, right? Why does that make sense? Because they can't go as close to each other, so they can't have as strong of a bond because they're bigger atoms. So what does that have to do with the band gap, right? Exciting an electron out of the valence band, what does exciting an electron out of the valence band even mean? That's sort of analogous to like partially breaking the bond, right? If I take something out of, if the valence band is like the bonding orbitals almost, right? So if I take something, an electron out of this valence band into the conduction band, it's almost like I'm taking an electron out of the bonding orbital. You can think of it analogous to taking an electron out of the bonding orbital and putting it in an anti-bonding orbital. So I'm almost like partially breaking a bond, right? And by partially breaking this bond, I'm allowing this electron that used to be between the bonds, that was localized in the bond, to now sort of be free to roam around the entire solid. So that was a lot of words. Just to clarify, if I have, a bond here, say silicon-silicon, right? And this solid is, has a bunch of silicon-silicon bonds all over, and they're all bonded in a tetrahedral arrangement and normal stuff like that. Now I input some thermal energy. What sort of visually does taking an electron into the valence, or from the valence band to the conduction band mean? That means I'm almost like taking this bond and kind of breaking it. And in a bond, I have two electrons, right? So I'm letting one of those electrons sort of break free and now roam around this entire solid. And now this bond is like a little bit weaker because there's only one electron-ish that's holding those silicons together. I'm just giving a very, wishy-washy explanation. But if you want to think about it in terms of, bond strengths, this is how you would think about it, right? I'm basically partially breaking the silicon-silicon bond, removing the electron from the bond and letting it roam free. And because of that, the energy it's going to take for me to excite from valence to conduction is going to be analogous to the energy it takes to break the bond. So germanium is the biggest, which means it has the weakest bond. Silicon has slightly, stronger bonds. And diamond, which is carbon, has, very, very strong bonds. So your band gap is going to decrease from diamond to silicon to germanium. Hopefully that made a little bit of sense, how breaking bonds is analogous to exciting an electron from your valence to your conduction band. All right, and now I want to talk about doping. So this is the other, we just talked about intrinsic semiconductors, and now we're going to talk about extrinsic semiconductors, right? So by me adding a little bit of impurity to some solid, how I can make it act like a better semiconductor. So what is doping, right? Doping is spreading small amounts of impurities through the solid, and this is going to result in an extrinsic semiconductor, right? So it's not an intrinsic semiconductor because I had to add something to it. And there's two sort of important parts of, or important types of doping, right? Or important types of semiconductors that I can create by doping. We have N-types and P-types. So an N-type semiconductor means that the impurity that I added contains more valence electrons than the atoms of the host lattice. And a P-type is the opposite. The impurity contains less valence electrons than the atoms of the host lattice. Okay? So how I like to remember this is, it's not entirely true, but a way to remember this is N-type is like negative. And it's not actually negative, but our impurity is going to have more electrons, right? More electrons means like quote unquote negative. And then we have P-type. P-type is positive, right? And again, it's not positive, but that means that we'll have less electrons in our impurity. Our impurity will have less valence electrons. All right. So And one example of this is doping silicon of an N-type, right, is doping silicon with phosphorus. Phosphorus has one more valence electron than silicon, so that's an N-type semiconductor. Whereas if I doped silicon with aluminum, that will be a P-type semiconductor because aluminum has one less valence electron than silicon. So how is this going to change my, diagrams? Right? How is this going to change my bands and my filling of the bands? That's an important question to ask, right? Essentially, if we look at, silicon and phosphorus, they're going to have really similar orbitals, right? They're going to have the similar 3s orbitals, 3p orbitals, all that good stuff that we already had dealt with when we looked at silicon on the previous slide, right? We had our valence band and our conduction band. That was unique to the mixing of the silicon atomic orbitals. If I add a little bit of phosphorus or if I add a little bit of aluminum, it's not really going to change my bands. It's not going to change how my orbitals mix together because I'm just adding a tiny bit of impurity. So all in all, right, my orbitals or my bands are going to look pretty similar. But what is going to be different is how much I fill the bands, because if I add phosphorus, I'm adding more electrons than I had before. So my bands will look the same, right? My energy levels of the bands are going to look the same, but the amount I fill them is not going to be the same. So if we look on this left diagram, we have an N-type semiconductor, and we look on the right diagram, we have a P-type. And here with N-type, you can see that we have additional electrons that need to fill the bands, right? Because phosphorus gave us more than the valence electrons we had before. So we're going to have a tiny bit of additional electrons, and because, remember, that the valence band was already full with silicon, these electrons are going to have to partially fill the previously empty conduction band. So we're going to have a little bit of electrons in our previously empty conduction band. And what does this do, right? What does this do to my conductivity? Conductivity is going to increase with doping, right? Why? Because now there's electrons that are in the conduction band, right? So these electrons that are in the conduction band basically can get excited really, really easily because they're already now, right, or how we talked about it before, is that now we have a conduction band that is partially filled. And what does that mean? Now that we have a conduction band that's partially filled, there are electrons in the conduction band, which means that these electrons can now, move around in the solid and be conductive. If we look at a P-type semiconductor, on the other hand, we have a similar phenomena that happens, right? So now, again, right, our bands are going to look really similar, but the way we fill the bands are going to change. And with a P-type, we dope it with an element that has less electrons, right, than our original silicon, for example, our original semiconductor. So before, if we had filled the valence band, now we're going to slightly not fill the valence band. So we fill it up until, this point, but the valence band that we used to call a valence band before now has some empty orbitals that electrons can still fill. So now this isn't even really a valence band, right? A valence band was defined as a full band. But here now, this is a conduction band. This is a conduction band because now we've made it partially filled because there are not enough electrons to fill the entire band. And because now we have electrons in a conduction band, it's going to be conductive, right? It's going to be way more conductive than before. So basically, essentially, by doping this, we're giving these semiconductors slightly metallic properties because we're making them so that they have partially filled conduction bands. All right, and now finally I want to talk about p-n junctions, or not finally, but I want to talk about p-n junctions. We'll talk about superconductors on the next slide. And p-n junctions are essentially when I take a p-doped semiconductor, an n-doped semiconductor, and I put them right together. And I put them in a circuit, right? So all I'm doing is putting a p-type semiconductor, right next to an n-type semiconductor. And you can see this in the diagram, right? We have p-type semiconductor to the left, n-type on the right. And I didn't really mention this in the previous slide, but we have this way of calling, you know, the sort of lack of electrons in our previously filled valence band. We give this a name. We call them holes. And we say because they're lack of electrons, we draw them as positives, right? And remember, the compound is still neutral. There's no net positive charge, but because these holes can act as charge carriers, right? Remember that these are like, because of these holes, we have now a conduction band. Those holes are sort of acting like charge carriers. So we draw them in as positive charge carriers. Whereas on the N side, we have extra electrons, which means those extra electrons are acting as charge carriers, so we draw them as negative. But remember, again, it's important to keep the distinction in your head that these PN junctions, or the P semiconductors and the N semiconductors, are both neutral, right? They're neutral, they're net neutral because they have the same amount of protons in the entire structure as electrons. But holes and electrons are the charge carriers that actually conduct the electricity. But what's interesting about PN junctions specifically is that current can only flow in one direction. And that direction is the way I've shown it here, right? If I put a battery like the positive electrode on this side and the negative electrode on the other side, these holes are going to be repelled by the positive electrode, right? Because the holes right now are facing the positive electrode on the left side, and the electrons are facing the negative electrode on the right side. So this positive electrode is going to repel these holes, pushing the holes to the right. The negative electrode is going to repel the electrons, pushing the electrons to the left. And now we have electrons flowing around the circuit, right, in a counterclockwise way, which is creating a current. Or we can think the same way as holes are going in a clockwise direction, creating a current. But say we had put this, you know, the opposite way. If I'd connected this with the negative electrode to this side, the positive electrode to the other side, and now put it like that, what's going to happen? If the p-type is connected to the negative electrode, these holes here are going to be attracted to the positive or to the negative charge, right? And the electrons in the n-type are going to be attracted to the positive electrode. So instead of the electrodes repelling the electrons and holes such that they moved around the circuit, now we're just going to have no current that flows because the electrons are attracted to the positive side, the holes are attracted to the negative side, nothing is going to want to move around the entire circuit. So if I hooked up the battery the other way, no current flows. And that's the important thing about PN junctions, is that it only allows current to flow in one direction. All right, now finally I want to discuss a little bit about superconductors and just give a little insight on why they're sort of important, right? So a really interesting thing about superconductors is that obviously their resistance is essentially zero. So a good application of this would be to reduce energy loss during transmission. So right now, like if you see like telephone wires or something outside, they're basically wires that are conducting electricity. But as they conduct electricity, there's power losses, right? Because there's current going through and there's resistance. So what's going to happen is that energy is sort of going to be dissipated, and that's just energy we can never get back, right? But if we have superconductors, we might be able to fix this issue. Energy losses are proportional to I squared times R. So this is a consequence of like Ohm's law or something like that, if you might have heard of that, but that's not really important. Essentially, all that's important is that the higher the current, the more energy losses we're going to have, and the higher the resistance, the more energy losses we're going to have. So this is sort of a tangent, but how we deal with the higher the current is we try to lower the current as much as possible to reduce energy losses, right? And we do this by using transformers that do something called step up the voltage and step down the current. But that's not really important. The important thing with superconductors is that we try to lower the resistance. And if the resistance is basically zero, our energy losses are going to be basically zero. So decreasing resistance means lowering our energy losses. So that's a, important way that we could implement superconductors if we could create these high temperature superconductors. So now let's, what is superconductivity? And again, just a more rigorous definition is the loss of electrical resistance when a substance is cooled below a characteristic transition temperature. So basically, as long as I go below a certain temperature, now it's basically the resistance is zero, right? And how we understand superconductors is by looking at something called Cooper pairs. So basically, if there aren't any Cooper pairs, generally we think of a metal. Like if I take a normal piece of metal and I analyze the electrons that are going through the metal, they're sort of all individually doing their own thing. They're flying in different directions because, remember, metals are conductive, so our electrons are all in the conduction band, so they can just sort of fly around the metal, in random directions, all doing their own thing. And what is that going to lead to? That's going to lead to a lot of electrons sort of bumping into each other, and they're going to, and when electrons and nuclei and all of these things are all moving in random directions and bumping into each other, what does that cause? That causes resistance, right? Because there's basically energy loss that's happening when all of these things are clashing into each other. But in a superconductor, we know that there is, sort of this lack of energy, of resistance. And that happens because of this phenomena called Cooper pairs. Essentially, these electrons, instead of all sort of going in random directions independent of each other, they're going to pair together. So we have these like two electrons, for example, that just, pair. And these are Cooper pairs. And when they pair together now and travel through the lattice, there's going to be a lot more or a lot less bumping into each other, right? Because now they're sort of paired and they aren't completely independent and random of each other. So this pairing helps us understand, what is happening in a superconductor that causes the resistance to suddenly, drop really, really low. Alright, so that's all I wanted to talk about in this video. Hopefully, you learned more about the applications of band theory to especially semiconductors, right? I think that's the most important thing in this video, is understanding how the band gap, changes and why it's important when we look at the properties of a semiconductor, and how does the band gap change, for different elements? Why would it change for different elements? All that sort of information. I think that's the most important part of this video. Hopefully, and insulators and superconductors are both they're fields of, or especially superconductors is a field of very, lots of research now, but important for Chemistry Olympiad. You don't really have to know too much about superconductors. But what I do think is really important is understanding everything about the semiconductors, the band gaps, the N-type, the P-type, the p-n junctions, all that sort of stuff. Yeah. So thank you guys so much for watching, and I'll see you in the next one.